apologize for last time. I didn't actually realistically expect that you'd get through the entire section. What I want to do today is kind of accelerate our, for obvious reasons, our discussion of synthesis and decomposition, and then sort of slow down a little bit more on the stuff that represents an addition to the stuff we did in grade 10. So we're going to talk about the same reaction types. We're just going to add stuff to them each time, okay? And that's most applicable to single replacement and double replacement. Not so much with combustion, but to a slight extent with synthesis and decomposition, okay? Nobody should have had a problem with the warm-up. That's right out of grade 10 science. But what I want to do is sort of focus on what's different about those types as we move into a grade 11 focus. So, in a nutshell, there are categories of synthesis and therefore categories of decomposition. They're effectively reverse of each other. The ones that you guys are most familiar with are, based on Science 10, is when two elements react to form a binary compound, okay? It doesn't have to be two elements. It could be more than two elements. It could be more than two species. It could be compounds. It could be elements of compounds. How we recognize a synthesis reaction is if we have one product. That's how we do it. We look to the right side of the arrow. What's on the left side of the arrow may be compounds, as it is here. Or it may be elements, as it is here and here. Here we have a very common synthesis reaction, formation of a halide. Notice metal, non-metal. Here we have another synthesis. This is formation of an oxide. This one is not only synthesis, it's also combustion. That's the simplest type of synthesis, where two elements react. It has to therefore make a binary compound. Synthesis reactions are usually exothermic, okay? But there are other categories of synthesis reactions, some of which I would expect you to predict products for, some not so much. When we classify metals or nonmetals in the periodic table, one of the criteria we use for that is what do their oxides do when they react with water. When a metal oxide reacts with water, it's a synthesis reaction, but we produce a metal hydroxide, namely a base. And you see that here. Potassium oxide and water makes potassium hydroxide. If I have, let's say I had lead 4 oxide reacting it with water, I'd make lead 4 hydroxide. Okay. Notice that the charge on lead here and the charge on lead here is the same, but if I make a hydroxide, that means it's a metal oxide in water. They're both compounds, neither are elements, but it's still synthesis because we got one thing on the right hand side of the arrow. When nonmetals react with oxygen, we produce acids rather than bases. These are a little trickier to predict, okay? And mostly they're difficult to predict because you can't look at a covalent compound, at least you can't yet, and say, okay, if it's SO3, then I'm going to make sulfuric acid. You have to be able to look at that sulfur and assign what's called an oxidation state. Here it's easy because I know it's 4+, but that's a real charge. When you assign oxidation states, you're assigning a real or imagined charge. And that's section 4.3. So I probably wouldn't expect you to predict the products of nonmetal oxides and water, all I would expect you to know is when a non-metal oxide and water react, we make an acid. When a metal oxide and water react, that synthesis generates a base. Okay? There's an even more involved version of a synthesis. That's when we react a metal oxide with a non-metal oxide. That's another synthesis event. And the formal name for the product is a ternary salt, meaning a 3-element ionic compound. So here's an example of that. When calcium oxide, which is a metal oxide, and carbon dioxide, which is a non-metal oxide, react, we get calcium carbonate. But again, that's tricky to predict. So I wouldn't expect you to predict that. I might expect you to balance it and identify it as synthesis. But if predicting products means you have to be able to do something that isn't basically part of the curriculum, then it's not fair. Okay? Because decomposition is effectively reverse of synthesis. If a metal oxide and water makes a base, then you decompose the base, you get the metal oxide and water. If a non-metal oxide and water make an acid, you decompose the acid, you must get the non-metal oxide and water back. And if most synthesis reactions are exo, then because energy is conserved, that must mean that most decomposition are endothermic, and they are. Okay? And notice the 3 examples of decomposition that Sherry gives you here. There's an acid decomposing non-metal oxide and water. If you turn this arrow around, you have the synthesis version. Okay? Here's a base, metal hydroxide decomposing metal oxide and water. If you react barium oxide with water, you get barium hydroxide. Here we have a ternary salt, a 3-element salt, iron 3 sulfate decomposing to a metal oxide, iron 3 oxide, and a non-metal oxide. That would be a little tricky to predict, as would be that. But it is a category of synthesis and therefore decomposition in the other direction. Sherry gives you a succinct table here. Now, I probably wouldn't expect this either way. Non-metal oxide and water, in the synthesis direction, it makes an acid. One, because it's one product, in that direction it's synthesis. If we turn the arrow around, it's decomposition. We return the non-metal oxide and water. This one I would think you should be able to predict. Look at the charge on the metal and the metal oxide, that'll be the charge on the metal and the metal hydroxide. So also taking the arrow away, whatever charge is on the metal ion here will be the charge on the metal oxide over here, and oxide is always 2 minus. Okay? This one I probably wouldn't expect you to predict, but this one, yeah. If we got a metal and a non-metal element, we have to make a binary salt. An ionic compound, metal non. That one's pretty straightforward. Okay? Now, Sherry gives a couple practice problems coming up, and we'll get there. The 3 simplest she starts with are the ones to which we add the least stuff in grade 11 compared to grade 10. And combustion's a good example of that. Combustion is usually a rapid reaction of an element or a compound with atmospheric oxygen, and it usually releases a lot amount of heat and light. The ones that we're going to focus on are burning a hydrocarbon, a carbohydrate, or an alcohol. All of them produce the same thing, carbon dioxide and water. Balancing all of them is done exactly the same way. Carbon first, hydrogen second, oxygen third. Okay? And let's have a quick look at some combustion reactions. Let's go to page 180. Look at 1G on page 180. That looks intimidating. C25, H52. That's candle wax, that's paraffin. It's obviously a hydrocarbon. But before you get intimidated by it, look at the numbers. Notice that this is CN H2N plus 2, right? And remember we said when we burn one of these, and that's a solid, I don't know if Sherry puts a state in there. Let's see, no she doesn't, doesn't matter. That makes it combustion, okay? Now, if we, let's say we react a metal with oxygen gas, that'd be synthesis, but it would also be combustion. Some reactions fit into more than one category. So when I burn paraffin, I get carbon dioxide gas, and the water is always in the form of water vapor because so much H2O. So that in a perfect world where all 25 carbons are fully oxidized, all the hydrogens are fully oxidized, you get nothing but carbon dioxide and water. In the real world, I'm gonna get some unburned hydrocarbons, I'm gonna get carbon monoxide, I'm gonna get carbon. So for example, if you put a piece of metal over the candle flame, it's gonna get black. And the fact that the candle flame is yellow tells you it's in complete combustion. But we're just gonna assume a perfect world here and complete combustion. Carbon first, hydrogen second, oxygen third. You're gonna do oxygen last for two reasons. One reason, because it's present in one place on the left, two places on the right, but you're gonna do it last because it's all by itself. And you might remember if we have a hydrocarbon of the form CnH2n plus 2, which this is, if n is an odd number, you won't end up having to multiply through by 2 when you balance it, okay? So 25 carbons, 25 carbons. We're gonna move on to D3. 52 hydrogens, 52 hydrogens. So 52 divided by 2 is 26. 26 molecules with 52 atoms. Now we do oxygen. 26 and 50 is 76, which divides evenly by 2, 3. Now, if that had been an even CnH2n plus 2, we would have to multiply through by 2. For example, this, that's called decane. It's actually a liquid, but don't worry about the states. So we burn that, we're gonna get the same thing. Carbon dioxide and water. And a lot of energy. Actually, the more carbons in the molecule, the more energy is released per mole. So 10 carbons, same order. 22 hydrogens, 22 hydrogens. Now we'll do oxygens and we'll find out that we have an odd number of oxygens. 11 and 20 is 31. So I gotta temporarily go 15 and a half. Then I multiply everything by 2, okay? So 2 of these, 31 of these, 20 of these, and 22 of those. With numbers that big, it's never bad. I did a check just to make sure they all match. 20, 20, 44, 44, 62, 40 plus 22. And notice that all the numbers are the smallest integers, which it has to be as well. In other words, if you could divide through by 2, do it. What about a carbohydrate? Now she says a compound made up of carbon, hydrogen, carbon, and oxygen. That's true. But that doesn't mean that every organic compound made of hydrogen, carbon, and oxygen is a carbohydrate. Alcohols have the same elemental composition. And if you, let's go to, let's see, top of page 181. Look at M. Now, conspicuous by its absence are the products. So, it's a compound containing carbon, hydrogen, and oxygen. Hello. Wanna come in? Yeah, come on in. Whether we call it a carbohydrate or an alcohol doesn't change the fact that we get carbon dioxide and water. It's just like a hydrocarbon, and we're gonna balance it the same way. The only thing we have to remember is that there's oxygen in the thing we're burning. So C3 H7OH, sorry, H5OH. And I don't know what that's called yet, because I don't know how those atoms are stuck together, but I know it's an alcohol. That OH does not mean the hydroxide atom. This isn't an ionic compound, it's a covalent compound. So we're gonna learn in organic chem that in this type of molecule, that's called hydroxyl. That makes it an alcohol, okay? When we burn it, and I'm not gonna put states in, but it's a liquid, we get carbon dioxide and water. Oxygen's in everything, so we're not doing it first. It's present as an element, so we're gonna do it last. 3 carbons, 6 hydrogens, 6 hydrogens. 3 times 2 is 6 plus 3 is 9. One of those here, we don't wanna put anything in front of that, because that'll screw up carbon and oxygen, carbon and hydrogen, so we only need 8 more. So we'll put 4 there, and okay? Now, why don't I know the name of that? You don't have to write this down, but there's one way that structure could look, where the OH is on an end carbon. And then, as we're gonna see in organic chemistry, if it's on this carbon, putting it here, here, or here are the same. And putting it on this carbon is the same as putting it on this carbon, because we just look at the molecule the other way around. The name of that compound would be 1-propanol. But that OH could also be here. And that's a different molecule. That's called rubbing alcohol, or 2-propanol. And that's one of the challenges of organic chemistry, is that just because you know the formula doesn't mean you know the compound. And just because there's 3 carbons, 6 hydrogens, and 1 oxygen, doesn't mean it's like that. It could also mean it's this, which isn't an alcohol at all. That's called an ether. And that's an entirely different class of organic compound. But if you burn that, or any variation thereof, you're gonna get the same thing, okay? What about a carbohydrate? Well, the most famous carbohydrate in this series would be glucose, C6H12O6, and I think she balances that combustion for you on the bottom of page 172. Let's burn table sugar. 312, 822, 011. Glucose is a monosaccharide, a simple sugar. Sucrose is a disaccharide. You've got 2 simple sugars stuck together. But when we burn that, we get the same thing. So again, let's do it. Carbon first, hydrogen second, oxygen third. 12 carbons, 22 hydrogens, Now let's look at the oxygens. We've got 24, and 11 is 35. 11 of them are over here, so we only need 24 more. So lo and behold, we're done. Okay. 100% of the time it works. Carbon first, hydrogen second, oxygen third. Okay. 12 carbons, 22 hydrogens, 11 and 24 is 35. 35 minus 11 is 24. 12 times 2 is 24. Easy. All right. There's octane, which is one of the components of gasoline. Notice it's CnH2n plus 2, and it's even. That's why we're going to end up needing a 2 in front of it. Here's glucose. Glucose will happily burn on a lab bench, except in cellular respiration, we don't want to light it on fire. So the little mitochondria of our cells, remember you guys in grade 8 called that the powerhouse? This is what happens in the mitochondria. What's it all for? To generate energy. But if we burn it, then all that energy's lost as heat. So what happens in the mitochondria is over a complicated series of biochemical events called the Krebs cycle, we slowly react the glucose with oxygen at various steps. And after each step, we suck energy out of that molecule and store it in something called adenosine triphosphate, ATP. So all of this is because when we're all done, we've got 38 ATP molecules. And that's energy money per living thing. That's where all that energy goes. We package it into something we can store. And then we use it to do everything. Move, think, respond to stimulus, run away from things that want to catch us and eat us. Our immune system, everything. Okay, that's what we need ATP for, and that's what aerobic respiration is. Technically, it's a combustion, but as Sherry tells us, it's slow combustion. Okay? We don't want to waste any of that energy in the form of heat. We want to put it in something we can spend to do stuff with. All right? Look at the practice problems here. I probably wouldn't expect you to predict this, and she doesn't. She just says balance it. But notice, one product, that's synthesis. Why would it be this? Why would it be phosphoric acid? Because that's a non-metal oxide. Okay? This is combustion. Notice that CnH2n plus 2, except N is odd. So that's methane. That's most of what comes out of here when I turn this on. So we won't have to multiply everything by 2. That is the decomposition of an acid. Carbonic acid decomposes to carbon dioxide, gas, and water. So non-metal oxide and water, that's this turned around. And that happens every time you take the top off a bottle of soda stream that you put carbon dioxide into. Carbon dioxide comes back out. The acid decomposes. Okay? So balance oxygen last here, balance oxygen last here, balance oxygen last here. Okay? In terms of what you should be able to predict, Sherry only puts it in a sample problem, I'm assuming, because this would be an unfair question on a test. This wouldn't be. That's combustion of methanol. That one's easy. CO2 and water. That's what I put in the milk jug when I shoot it across the room. Okay? That one you should be able to do too. This is obviously decomposition, right? Based on the formula, what's the charge on scandium in this compound? 3+. Does that make sense that it's going to be 3+? Yeah, look at where it is in the table. It's got 21 electrons. If it gives away 1, 2, 3, looks just like argon. Because it's a metal hydroxide. When I decompose a metal hydroxide, I get a metal oxide and water. And the charge on the scandium in the metal oxide is going to be the same as in the hydroxide. So what you have to do is recognize this as decomposition of a metal hydroxide. Scandium oxide then would be this and water. In this direction, it makes a base. In this direction, it makes a metal oxide and water. Do oxygen last. 1 scandium, 2 scandium here, so I need 2 there. Now I do hydrogen, 2 times 3 is 6. 3 and 3 is, 6. Done. Okay? Nothing to it. This one, though, is a little trickier. And why it's kind of unfair to expect you to do it if you look at what to think about. Reaction 2 is combining a non-metal oxide with water. This must form an acid. Okay, we get that. Determine the correct formula for the acid by combining the hydrogen ion with an oxyanion of boron. In other words, a negative ion that has boron and oxygen in it. but this is where it's a little beyond you guys. To determine the oxyanion of boron, calculate the oxidation number on boron in B2O3. Well, it's not an ionic compound. So what you're doing when you assign this, which by the way is a section we're not doing, you pretend that all bonding is ionic. And you begin with assuming that oxides are always 2 minus. So if you pretend that's an ionic compound, if each oxide is 2 minus, then in that compound, 3 times 2 minus gives 6 minus, right? And if this is a neutral compound, then that must mean the charge on boron would have to be +3, right? And she explains that here. Okay, that makes sense. But this next line is also something that you wouldn't necessarily be able to arrive at. Therefore, the oxyanion of boron is boring. I know that, but how would you guys know that? That just because the oxidation state of boron is +3, and notice it's not 3 plus. If the charge comes in front of a number, that means it's an oxidation state, which means in this case it's an imagined charge. So you see how this is a little unfair. And just because it's that, why does it mean that's the end? You guys don't know enough chemistry to do that. So why is Sherry asked it? I do not know. And that's why I wouldn't expect that, okay? If I gave you that and said classify it and balance it, fine. But I wouldn't just give you an arrow and say good luck, all right? And if I can't expect the arrow in that direction, I can't expect the decomposition in the other. If you look at what she actually has asked you to do, all of those are fair. Okay. This is obviously decomposition, right? Because there's only one reactant. And what we're decomposing is a binary compound. So that has to give 2 elements. What a lot of students will do when they see that is they'll go, okay, that gives iron 2. Don't ever put a subscript next to another. They're never diatomic. Okay? It's going to give iron and oxygen, which is diatomic. Every metal is a solid at room temperature except mercury. Oxygen is a gas. Least common multiple of 2 and 3 is 6. So put a 3 there, a 2 there, and there, and we're done. Notice C3H7OH, alcohol, carbon dioxide and water, carbon first, hydrogen second, oxygen third, number 2. What about this one? That's a metal oxide, right? Metal oxides and water make bases. This is a fair question. What's the charge on a silver ion? Well, look at it here, 1 plus. It's also on your table. So if silver oxide plus water is going to make silver hydroxide, the charge on silver is going to be exactly the same. 1 plus. And then we just bounce. 2 oxygen last. 2 silver, 2 silver. 2 hydrogens, 2 hydrogens, 2 oxygens. Done. What about this? That's a metal hydroxide, right? That's a base. That's the reverse of this. What's the charge on the lead ion here? 4 plus. So it's going to have the same charge in the oxide on this side. So here we react a metal oxide and water to get a base. Here we decompose a base to get a metal oxide and water. So we're going to have lead 4 oxide plus water. Once again, do oxygen last because it's everywhere. 1 lead, 1 lead. 4 hydrogen, 4 hydrogen, 4 oxygen, 4 oxygen. Now those are all fair questions, okay? These are going to take a little longer. So we're gonna add a couple things to this. Single replacement reaction. Less commonly known as single displacement, involves a reaction between a compound and an element, so that the element replaces an element of the same type, meaning a metal can only replace a metal in a compound, a non-metal can only replace a non-metal in a compound. What we didn't do last year in grade 10, because you guys were too young, your brains were small, you were stupid, we just introduced stuff but didn't explain it. Now you're smarter. Now you're enlightened. We're gonna do two things here that we didn't do last year. One of them Sherry doesn't do, but I'm gonna do anyway. But the second one is what's on the next page, the activity phase. So, during a single replacement reaction, a free, uncombined, and I would maybe say neutral element, has to be neutral, kicks out a combined element and takes its place. The ion that it replaces, or the element that it replaces, has a charge. So if a metal replaces another metal, a neutral metal atom replaces a positive metal ion in a compound. A non-metal element replacing a non-metal in a compound, the non-metal that it's replacing has a negative charge. And here's an example of metal replacement. The potassium starts out as two neutral atoms. It's replacing a copper 2 ion in solution. When it's done, the potassium atoms have become two potassium ions, and the copper 2 ion has become a copper atom. Here's a non-metal replacement. Bromine, two neutral atoms stuck together, are replacing two iodide anions in this solution. Not the sodium, the iodine, because non-metal can only replace non-metal. When the reaction's over, the two bromine atoms have become two bromide anions in solution, and the iodide ions in solution, the negative ions, have become two neutral atoms. What I want to do is dissect what's happening in this one and this one. Okay? So, that AQ means that compound is dissolved in water. In other words, those ions are apart. So I'm going to write that this way. 2 potassium, and that little 0 reminds us it's neutral. Okay? That solid is added to a solution of copper 2 nitrate. And that AQ means the copper 2 ions and the 2 nitrate ions are separated from each other. Okay? That's what that AQ means. So in this solution, that's the ions that are there, right? On the right-hand side, we now have 2 potassium ions in solution. Now they have a charge. And notice, nothing has happened to the nitrate. They're still in solution. But the copper 2 ion that started out in solution, and we're going to see in the lab we do at the end of this chapter that that's a nice blue color, copper 2 and 1, okay? That has become solid copper now. So the solution that we started out with had those things in it. The solution that we end with have those things in it. Notice the nitrate didn't change at all. It started out as 2 ions in solution, it ended as the 2 ions in solution. We need it there because there's no such thing as a charged compound. So nitrate, why would I have picked, or why would she have picked copper 2 nitrate? Because nitrate salts are always soluble. Anytime you need to get a positive ion in solution, pick a nitrate salt. It always dissolves in water. But in terms of the nitrate changing chemically, it doesn't. It doesn't do anything. And chemists have a name for ions that don't participate. We call them spectator ions. So let's get rid of the spectator ions in that equation and focus only on the things that change. So let's get rid of the 2-nitrate here, and let's get rid of the 2-nitrate here. So that's the business end of this equation. The potassium atoms are replacing the copper 2 ions from solution, producing potassium ions in solution to copper atoms, correct? So far so good? Let's just write those one at a time. So we start off with potassium, neutral potassium. When the reaction is completed, we have 2 potassium ions in solution, right? That's what happens to the potassium. Which tells us that when a metal replaces a metal ion, the metal that replaces it starts out neutral, ends up with a positive charge. How does that happen? How would a potassium atom with no charge become a potassium ion with a 1+ charge? What has to happen to that potassium atom? Go ahead.
Like change like how many electrons it has?
Okay, but how? Specifically. Is that gaining electrons or is it giving them away?
Losing?
Has to. Does that make sense? The potassium would want to give an electron away? Yeah, it's got 19, it wants 18. That's all the alkali metals ever do. So a potassium atom becoming a potassium 1+ ion has to lose an electron, right? And there's 2 of them. So that's what's going on with the potassium. It's losing 2 electrons. What's happening to the copper? The copper starts out as 2+ in solution, and it ends as a neutral copper atom. What's the only way that can happen? Louder?
Gains electrons.
How many? 2. So here's the point. When a metal replaces a metal ion, the thing doing the replacing loses electrons. The thing getting replaced gains them. This type of a reaction where electrons are transferred is called oxidation reduction. I'm mentioning it because we're not going to do section 4.3, but every single replacement reaction is an oxidation reduction. It's an electron transfer reaction. Electrons are transferred from the potassium that loses it to the copper 2 that gains it. Now, because they're in the same solution in physical contact with each other, that electron transfer happens directly. The potassium atoms lose electrons to the copper 2 ions. But if I can somehow construct an apparatus where the electron loss is physically separated from the species where electrons are gained, and if I make those electrons travel through a wire, they can do work for me. And that's an electric battery. An electric battery has a negative electrode that is part of a chemical system where electrons are lost. The positive electrode is where those electrons go and they undergo a chemical change where they're gained. And the 2 always have to happen together. Something has to lose the electrons, something has to gain it. This electron loss and gain, each of these things are called half reactions. And a loss of electrons is called oxidation. And a gain of electrons is called reduction. And that may seem odd to call it reduction when electrons are actually gained, but that reduction speaks to the magnitude of the positive charge. It always goes down when electrons are gained, okay? Now, I'm not going to focus in detail on oxidation, reduction, or redox reactions, but there's an easy way to remember which is which. Oxidation is loss, reduction is gain, like oil rig. Or if you want another way, loss of electrons is oxidation, gain of electrons is reduction. And that's affectionately summarized by Leo the Lion goes grr. About 20 years ago, there was a grade 9 student standing with her friend in front of the bulletin board where I put up solutions to some Chem 11 and 12 worksheets. One of them was Diana Hunter, her friend was Lindsay Law. Diana looked at the board and goes, "Oh, that looks hard." And I happened to be walking by the bulletin board. I said, "No, it's not hard, take it. You'll find out it's not hard." Dr. Diana Hunter is now a neuroanatomist up at Simon Fraser University. When she graduated, the day she wrote her Chem 12 provincial final, which by the way back then was worth 40% of your final grade, and you had to write it, she gave me this. Leo the Lion says grr. And you could tell the Chem students, or the Chem 12 students, when they were writing their Chem test, near the end of the test, where the redox section is, you'd walk by them and you'd hear them going grr, right? Because they were remembering gain of electrons as reduction. And she was kind of pleased to know that I still have this thing. That's from, gosh, maybe 2004? Maybe 2004? Anyway, we're not doing oxidation reduction in grade 11. If you're interested in it, it's a topic in Chem 12. If I haven't retired next year and I'm teaching Chem 12, you'll learn about it. But section 4.3 is an introduction to redox. So if you're intending on taking Chem 12, maybe you want to read that section. Okay? Every single replacement reaction is redox. Okay? Double replacement aren't, but single replacement are. And redox is always electron transfer. Yes? Let's do the same thing with this one. Remember here, the metal that does the replacing loses electrons or is oxidized. The metal ion that gets replaced is reduced. That's opposite for non-metal. Single replacement. Am I going too fast? Are you guys okay so far? Knowing I won't make you do this on a test. I'm just adding some stuff so it hopefully makes sense to you. So let's do the bromine reacting with the sodium iodide solution. Notice that in each of those examples, metal replacement or non-metal single replacement, the compound's in solution. Usually that has to be the case. Usually you have to have the ions separated in solution. Okay? So we're going to do the same thing that we did here. We're going to pull apart the ions that are in solution. We're going to write them apart. So we have two bromine atoms that are neutral. They're stuck together in a diatomic molecule. Notice Sherry puts an L there because bromine is one of the two elements in the tables of liquids at room temperature. It's a dark brown liquid. The other one is mercury. So bromine is reacting with a solution of sodium iodide. And that AQ means the two sodium ions are separated from the two iodine ions in solution. Okay? So that's what's in that solution. When the reaction is completed, the two sodium ions are still there in solution. But now instead of two iodide ions in solution, we have two bromide ions in solution. And instead of two bromine atoms stuck together, we have two iodine atoms stuck together. And iodine is a solid at room temperature. Okay? So, of that trio on each side, which hasn't changed? Which one did nothing happen to it?
The sodium?
Sodium. So sodium is a spectator ion. What is its role? It only guarantees that that thing is soluble. So in the same way, if you ever want to get a positive ion in a compound to dissolve, pick a nitrate salt. If you ever want to get a negative ion in a compound and guarantee that thing's soluble, pick a sodium salt. And I'll explain why that is when we get into double replacement. So let's remove the spectator ions from this event, because nothing's happening to sodium. So get rid of that. And it's like removing like terms in an algebraic equation, okay? Now let's separate the bromine from the ion. Bromine starts out as two neutral atoms stuck together in a diatomic molecule. It ends as two 1- anions in solution, right? The two iodide ions that begin in solution end as two neutral iodine atoms stuck together in a solid form. So let's ask ourselves the same questions about the bromine and the iodine as we did the copper and the potassium. So what's happening to this? How does a neutral atom become a 1- ion? What's happening to each of those two bromines? Are they losing them or gaining them?
Gaining.
Each bromine atom has to be gaining an electron, right? And there's two of them. Now, contrast that with the metal single replacement. In the metal single replacement, the thing that did the replacing lost electrons. That's all metals do chemically. They give electrons away. But here, the non-metal element doing the replacing was gaining electrons. And remember, gain of electrons is called reduction. That's the GER. Okay? Here, the thing getting replaced doesn't have a positive charge, it has a negative charge. So for it to get neutral, it has to lose electrons. So in a metal replacement, the thing getting replaced gained electrons. But here, the thing getting replaced loses electrons. And that's Leo. Okay? Loss of electrons is oxidation. It's still electron transfer, but the direction of electron transfer is opposite. In metal single replacement, the thing getting replaced got the electrons from the thing doing the replacing. Here, the thing getting replaced is giving electrons to the thing doing the replacing. It's still electron transfer, but it's in the opposite direction. So the thing doing the replacing undergoes reduction. The thing getting replaced undergoes oxidation. It's still reduction. And notice if you add these two things together, which is the same case in the previous example, the electrons cancel, and you get that. Okay. Some of you, not just you, some of my grade 12s, are in the habit of leaving charges in. There are reactions that are virtually impossible to balance by inspection. You guys won't have to do them, but in grade 12 you will. And the only way to balance those things is to keep track of electrons. Bookkeep electrons. So if you're in the habit of leaving charges out, you're doomed if you're doing redox. Because it's all about being meticulous with charges. And in the same way that there's a conservation of mass law, which helps you balance atoms, there's an equally rigorous conservation of charge law. Charge has to balance too, okay? You'll never see electrons in an overall chemical reaction. In a redox reaction, the total electrons lost always has to equal the total electron gain. And that's one of the ways we employ, one of the things we do to end up balancing these things. I'm not gonna ask you to write oxidation half reactions or reduction half reactions. I'm only bringing it up because every single replacement reaction is redox. Whereas double replacement are not. Even though the name sounds kind of similar, double replacement do not involve a change in the electronic nature of structure. They're easier in terms of chemically what's going on. Notice what Sherry puts in the middle here, hydrogen replacement. Sodium is replacing hydrogen from water. Notice she doesn't write water as H2O. She writes it as HOH. And the reason is that's the hydrogen that gets replaced. Okay? And she tells you down here. Notice that when hydrogen is being replaced in water, not all elements will do that, but sodium will. It's a good idea to think of water's formula as hydrogen hydroxide. This makes it evident that the product is a hydroxide of the metal, or a base, rather than an oxide. In other words, if you wrote water as H2O, you might think that hydrogen's getting replaced. So you might go, okay, sodium plus water, I'll replace the hydrogen, I'm gonna get sodium oxide and hydrogen, which would be wrong. Only one of the two hydrogens gets replaced, and it's effectively, we're pretending that water is a hydroxide, even though it's not. Okay, that's why she wrote it. Some elements will replace hydrogen from water, not all will. And that's the other thing we're gonna add to this. In Science 10, there was no mention that some single replacement don't occur. Some things will replace some things won't. And how do you know what will or what won't? Well, that's the next page. It's called the activity series, or chemical reactivity series. You're never gonna have to memorize this table. I'll give it to you, but you do have to know how to use it. In a nutshell, any metal on the left will replace a metal from a compound underneath it. But a metal underneath another metal will not replace it. So for example, potassium will replace zinc from a compound, but zinc will not replace potassium. Notice that all of these are metals except that one. And she put hydrogen in bold, in all caps, with a little asterisk. If you look in your periodic table, even though hydrogen isn't a metal, it's sitting above the alkali metals. If you look at this periodic table, it's in two places. It's above the alkali metals and also above the halogens. Why? Well, it's above the alkali metals, it's not a metal, but in a lot of its compounds, it forms a hydrogen plus one ion, which is the way it is in all acids. If we stick it to a metal, it forms a hydride, which is a 1- ion, like all the halogens. But if hydrogen has a positive charge, the positive charge means what's replacing it can see it as a metal, because metal ions are always positive. The metals above hydrogen will replace hydrogen from an acid, because in acids, hydrogens exist as positive ions. But that little asterisk gives you a little qualifier. Hydrogen may be displaced or replaced from most acids by all metals above it. However, hydrogen may only be displaced from water by metals above magnesium. So if you put magnesium metal in water, it's going to get wet. That's it. But if you put sodium in water, you're going to get a reaction. It'll replace the hydrogen from water, making sodium hydroxide and hydrogen gas. And it's also exothermic. And as you travel down the alkali metals, the same reaction happens, it just gets more violent. Notice lithium and potassium are here. She hasn't put rubidium or cesium, probably because they're not as common, but they're more reactive. So if I put a little fingernail's worth of cesium in a glass of water, the water blows up. because the hydrogen's released so fast in the exothermic reaction that it ignites, okay? Given this table, you should be able to predict which single replacement reactions occur for metals replacing metals, potentially, or non-metals replacing non-metals. This one's easy to remember, it's the same order in the periodic table. So fluorine will replace anything. Iodine won't replace anything. Chlorine will replace bromine and iodine, but it won't replace fluorine. Bromine will replace iodine, but not chlorine and fluorine. That's the idea. And Sherry gives you a little quick check down here to see if it makes sense. Will sodium replace aluminum from aluminum chloride? What? Well, look at that. That's gonna be single replacement if it proceeds, right? If this is a metal, look at that. Is this above that? Yes. So we're gonna make sodium chloride. And I know it dissolves in water, and I'll probably won't be able to get to it today, but we will next class. And aluminum. Aluminum's a solvent in temperature. No, never diatomic within a metal. Then we just balance it. 3 chlorines, 3 fluorines, 3 sodium, 3 sodiums. Right? Done. What about number 2? What'll happen there? Ask yourself the same question. Is copper above potassium? So what do you write on the right-hand side of the arrow? No reaction. Nothing happens. And if it won't go in this direction, it means it will go in the other. In other words, potassium will replace copper. Copper won't replace potassium. Will that one proceed? Fluorine's above iodine. Notice fluorine's a non-metal, so you look at that. Remember that every halogen is diatomic. Also remember that every negative charge in a halogen is 1 minus. So this will be lithium fluoride. I don't think she's expected states, but it is soluble. And then the iodine is diatomic, and it happens to be salt. So 2 iodine, 2 lithium, 2 lithium, 2 fluorine, 2 fluorine, done. What about number 4? Notice how she's written water, that's a clue. Calcium's above hydrogen, fine, but is it also above magnesium? Yeah. So? Just in case this idea is not perfectly clear, let's write water as that. Hydrogen doesn't have a positive charge, but calcium sees it as that. In other words, it sees it as a metal. So the calcium will replace the hydrogen. Hydroxide as an anion is 1 minus, which will give this, because calcium's 2 plus. Calcium hydroxide isn't soluble, but again, I'll get to that soon. And the hydrogen that's released, hydrogen is diatomic. So now we balance it. And let's balance hydroxide as if it was a polyatomic ion. Let's things together, 2 hydroxide, 2 hydroxide, and now we're finished, because that gives me 2 hydrogens. Okay. Now, had you written water as H2O, you probably would have got calcium oxide and hydrogen, which would be better. Okay? But that only happens because calcium is above magnesium. And it's a group 2 metal that reacts with water, the other group 2 metals don't. Okay? Make sense? Okay. Now, I never expect you to memorize this, but this is what you use anytime you're predicting products for a single replacement reaction. I would give it to you on a test the same way I give you your periodic table or your table of elements. Now, the vast majority of single replacement reactions have to have the compound in water. But there's a notable exception to that, which is kind of a famous reaction. If you look at the table, is aluminum above iron? So aluminum, which is a solid at room temperature, will replace iron. iron 3 oxide, is effectively rust. It will replace it even when they're both solids to form aluminum oxide, which is also a 3+, and iron. But so much heat is released that both this and that are liquid. This is called the thermite reaction. And a thermite mixture is powdered aluminum and powdered granular iron 3 oxide. If you light this thing with a magnesium fuse, so much heat's released that both the iron and the aluminum oxide are produced as melted liquids. Iron has a melting temperature north of 1800 degrees Celsius. Aluminum oxide is even higher than that, 2000 degrees Celsius. But this generates temperatures 2500 degrees Celsius. And once you start it, you can't stop it. Railroads used to use it, some still do, to weld railroad ties together. There's a little apparatus you sit over the joint of the railway ties. You ignite the thermite mixture, usually with a magnesium fuse, and liquid iron pours out from the bottom of this thing, welding the tracks together. There are armor-piercing rounds that the military uses that are thermite rounds. And when the round is launched from the cannon or the fighter jet, the thermite's ignited. By the time it gets to its target, it will melt through any armor plate. That's how hot it is, okay? I can't show you thermite. If I did it on the table, it would melt through the desk, through the floor, through the ceiling, into the French classroom underneath, which wouldn't be a bad thing, into the floor, into the basement, okay? If I did it outside, I don't even know if it's legal to do it outside in the residential area, but usually when it's done outside, it's done on a bed of sand. The sand is vitrified, it turns into glass. You can Google the thermite reaction. There's a group of British chemists called brainiacs. And if you Google
melting to the car.
Thermite versus car, because they're British, they decide to destroy a French car. Okay?
Do not attempt.
First, they ask themselves, well, here's liquid nitrogen at minus 198. Will it extinguish thermite? They try that. Then they take the thermite and they burn through the engine of a little old POS Renault, right through the engine. Then the car's still there, but they decide to light the thermite over the gas tank and blow the car. The point is, you get a better idea about what this whatever. Okay.
This is thermite. It's a powdered mixture of iron oxide and aluminium, which when ignited burns at 2,500 degrees Celsius, which is very, very hot. This is liquid nitrogen. It's specially stored at minus 198 degrees Celsius. That's 163 degrees colder than the North Pole in winter. But is it cold enough to neutralize the intense heat of thermite? Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Just line the touch paper and stand well back. The fuse triggers the irreversible thermite reaction. As scorching hot meets freezing cold, a fierce battle rages. The smoke clears, and incredibly, nothing remains. As the thermite burns at 2,500 degrees, it releases a raging torrent of molten iron, which rains down upon the liquid nitrogen, boiling the glacial mixture away in a plume of vapor and melting the cylinder, leaving just a puddle of white-hot iron. A clear victory for thermite. So there you go, Dan. Adding something cold to thermite doesn't cancel it out. It just makes it angry. Thermite. You won't like it when it's... This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of the car. It's basically a huge lump of metal, and well, it's very hard to melt. Lucky then, the Brainiacs have plenty of thermite, especially packed into the slow release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clean through, it seems only fitting to have a go at the petrol tank. Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Popped onto the roof, directly above the fuel tank, top up, and just 4 feet of family car stands between the thermite and 8 gallons of petrol. Light the touch paper and stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. Its 2,500 degree heat igniting the expanding petrol in a devastating fireball, leaving behind a car that won't be going very far anytime soon. So there you go.
I don't know what that is. Gift cord. What is it? It was chemistry. What the hell? Alrighty then. Now, the next
Why is this
type we're going to look at is double replacement. Well, we're not going to get much time. Double replacement, although the name sounds similar to single replacement, does not involve electron transfer. It's not readable. Last year in Science 10, double replacement was only considered in the form of 2 solutions being mixed where you get a precipitate. Okay? That's one of 3 different types of double replacement. Okay? A double replacement reaction is a chemical reaction between 2 compounds that trade cations or anions with one another. So you begin with 2 ionic compounds. You mix them. New ion combinations see each other in that mixture. So the positive ion in one solution sees the negative ion in another, and vice versa. In one type of double replacement reaction, you get a precipitate, okay? That's the kind of move from you have to see a salt, at least one salt. In some cases you'll see 2, but you have to see at least one. We didn't classify neutralization as double replacement, but it is. That's acid plus base gives salt plus water. We don't call it just double replacement though, because in this form of double replacement, 2 ionic compounds make 2 ionic compounds. One of them's a salt, at least. In this type of double replacement, an acid and a base makes a salt and water. Only one of the 2 is ionic, one of the products, and we may not see a precipitate at all. Okay? This one's a little trickier. We didn't talk about this either last year. This is where 2 compounds are mixed, switch the ions like you always do, but then one of the products turns into 2 things, a gas and water. And there's 2 kinds of that, and we're going to leave that till the end, okay? Let's look at the ones you guys are most familiar with first, assuming you remember anything from grade 10. That's precipitation, all right? Here's an example of a precipitation double replacement. AQ means this dissolves in water. So sodium, anything plus sodium dissolves in water, so that's table salt. Anything plus nitrate dissolves in water. But when those two solutions are mixed, when the silver ion in this soluble solution sees the chloride ion from that soluble solution, those two aren't soluble. And that's the precipitate that we get. This one is still soluble. The obvious question is, how are you gonna know which one's solid and which one isn't? Well, Sherry tells you here that predicting which salt will precipitate requires information about the relative solubilities of the products. A future chapter will provide this information. Well, let's go to that future chapter. Let's go to chapter 7, that's not it. Let's see. That's
Oh,
not it.
hell no. What the This is 8.1.
I'm drawing your attention to the table on page 363. Let's see.
Oh, no.
Now, just like the activity series or chemical reactivity series, you wouldn't have to memorize this. If I asked you to indicate the states, then I'd have to give you this. Even though you don't have to memorize it, it might help to know how it's structured. So, we have common negative ions here, common positive ions here, and here, whether the combination is soluble or low solubility. What does soluble mean? Usually it means I can get a solution of at least 0.1 molar to exist. If I can't get enough of these things in solution to get a 0.1 molar solution, then that compound is low solubility. The first 4 rows, the combinations are all soluble. So, every alkali ion is soluble with every negative ion. So there's no such thing as an alkali compound that doesn't dissolve in water.
Good afternoon, staff and students. Can Hannah Batista please come down to the main office? Thank you. Now, let us prepare ourselves for the end of day prayer. In the name of the Father, Son, and the Holy Spirit. Dear God, we pray for the fruits of the Holy Spirit: love, joy, and peace, patience, kindness, goodness, faithfulness, gentleness, and self-control. We know that these fruits are life's greatest blessings. May we use these blessings in order to help find faith in your word. Amen. St. Thomas More, pray for us. Blessed Edmund Rice, pray for us. Live Jesus in our hearts forever. In the name of the Father, Son, and the Holy Spirit. Amen.
You guys are almost caught up to their classes, not totally yet, but if you could read the bottom half of that last page, in other words, the neutralization and the gas formation, then have a look at some of the review questions. Notice how Sherry scaffolds it. She gives you the formula equation, reactants and products. All you do is balance it and classify it. Then she gives you the formulas without products, classify it, complete and balance it. Then she just gives you the names of the reactants. So try a few of those. We'll complete our discussion of solubility table and finish the section next time. Next time, I'll also give you back your tests. I'm not going to record grades. I'll record the grades after I'm giving the test up, all right? So don't wait in front of the computer waiting to see if I put it up on PowerSchool over the weekend. I won't, all right? See you Tuesday.